Okay, today we're diving into a really interesting paper, quite a shakeup actually. It's called Reasoning Models Reason Well Until They Don't, and it comes from researchers at the University of Washington and Purdue. Let's jump straight into the one-minute summary because this is something you'll want to get your head around.
Absolutely. So you have these advanced models, large reasoning models, or LRMs. These are basically LLMs fine-tuned specifically for complex arguments, verification, that kind of thing. And on the standard tests, the existing benchmarks, they look amazing.
Like really good scores, right?
Oh, yeah. We're talking 96%, even up to 99% accuracy. They seem like reasoning masters.
But, and this is the big but, the researchers felt those existing tests maybe weren't, well, tough enough.
Exactly. So they created their own benchmark, a new one called the Deep Reasoning Dataset, or DeepRD. And the key thing here is it's synthetic, totally scalable in complexity.
And the headline finding.
It's pretty stark. When you test these same high-performing LRMs on DeepRD, as you ramp up the complexity, their performance doesn't just dip. It completely tanks, like falls off a cliff down to near zero accuracy.
Wow. Even on tasks that seem pretty fundamental, like proof planning.
Yep. And crucially, this isn't about the models running out of memory, context windows or token limits. The paper argues it's a fundamental failure in generalization.
So they ace the easy stuff, the kind of low-complexity examples common in training data.
Right. But that long tail of genuinely complex real-world problems, that's where this hidden failure point shows up. And it's a massive drop.
Okay, so our mission today is to really unpack how they built this DeepRD, what makes it complex, understand these limits they found, and importantly, what does this mean for actually using these models for things like automated research, law, maybe even maths.
Let's dig in.
So let's set the scene first. This whole idea of LRMs. We've seen huge progress in LLM reasoning, right? A lot of it attributed to techniques like RLVR reinforcement learning with verifiable rewards.
That's the one. It's a way to fine-tune a base LLM, making it supposedly better at reasoning, turning it into one of these specialist LRMs. The hope was this created genuine generalized reasoning skills.
And the evidence seems strong based on those benchmarks you mentioned earlier, like NLGraph Hard.
Exactly. Models like DeepSeek R1, OpenAI's O3 Mini, they were getting near-perfect scores on NLGraph Hard. So naturally, the conclusion many drew was, okay, they've cracked it, generalized reasoning is here.
But this paper pulls back the curtain on that. It suggests those high scores were maybe a bit misleading, because the tasks themselves weren't that complex.
Precisely. When the researchers actually analyzed the structure of the problems in NLGraph, particularly the hard ones, they found something surprising.
What was that?
The required lookahead was incredibly shallow.
Lookahead. Define that for us.
Right. Lookahead basically measures how many steps into the future the model needs to correctly see or plan just to figure out the very next correct move from the starting point.
Okay, so not the total solution length, but the depth of planning needed for step one.
Exactly. And in those NLGraph hard problems, which often use randomly generated graphs, the expected lookahead turned out to be mathematically tiny. It's bounded at approximately 1.805.
Wait, hold on. 1.8 steps.
Yep.
So most of the time, the model only needed to look maybe one, maybe two steps ahead to get the first move right.
That's the implication. They were acing tasks that didn't actually require deep, multi-step planning or search.
So they were solving problems that looked complex, maybe the graphs were big, but structurally, the decision-making was simple.
That's the core argument. And that's why they needed to build the Deep Reasoning Dataset, DeepRD. They needed a way to crank up the actual structural complexity in a controlled way.
Okay, so tell us about DeepRD. How do they engineer this controllable complexity?
They focused on two key metrics. The first, and probably most important, is this lookahead, L we just talked about. They defined it formally using breadth-first search, or BFS. L is the number of BFS iterations needed to find that single correct next node on the path. And crucially, they could scale L, starting from 2 and going way up, all the way to 800 in their tests.
L equals 800. That means the model has to correctly project 800 steps into the future just to decide the immediate next step.
In essence, yes. It's a measure of how deep the planning needs to be right from the start. It really tests that forward planning capability.
Okay, that's L. What was the second metric?
The second metric was the number of branches, B. This is simply how many possible next steps or outgoing nodes there are from the starting point. They scaled B from 2 up to 4, 8, and 16.
And why is B important? What does that control?
B basically controls how easy it is to guess correctly. If there are only 2 branches, B2, you've got a 50-50 shot just by guessing randomly for the first step.
Right.
But if B16, your random chance drops to just over 6%. So a higher B makes random guessing much less effective. It forces the model to actually reason to find the right path, otherwise its accuracy plummets purely due to chance.
Makes sense. So you have lookahead L testing the depth of reasoning,
Right.
and branches B testing the ability to distinguish the correct path from alternatives.
Exactly. And they use this DeepRD setup to test both standard LLMs like V3 and 4.0 and these specialized LRMs, R1 and O3 mini, on 2 main tasks.
What were the tasks?
Task 1 was symbolic graph connectivity. Pretty straightforward. The model gets a graph described as a list of connections, like A connects to B, B connects to C, and it has to output the entire path from a start node to an end node.
Okay, find the full path.
Yep. And task 2 was natural language proof planning. Here, they took the same underlying graph structure but described it using natural language axioms, things like, if A is true, then B is true. If B is true, then C is true.
So translating the symbolic task into something more like logical deduction in words.
Precisely. But because these proofs could get very long and complex, for this task, they simplified the output. They only asked the model to produce the next correct proof step.
Ah, okay. So that directly maps back to just finding the correct next node in the graph structure.
Exactly. It isolates that crucial first reasoning step under natural language conditions.
All right, so they have the setup, the metrics, the tasks. Let's get to the results. You said the performance collapse was abrupt.
Shockingly so, especially on the symbolic graph task first. If you look at the graphs in the paper, it's not a gentle slope downwards, it's a cliff.
A literal performance cliff.
Absolutely. For all the models, they tested the base LLMs and the specialized LRMs. Once the complexity, defined by L and B, hits a certain point, the accuracy in finding the full correct path just drops to 0, completely collapses.
And does it affect all models equally?
Well, the LRMs, the ones fine-tuned for reasoning, like R1 and O3 mini, they definitely hold out longer. They resist the collapse until higher complexity levels compared to the base LLMs like V3 or 4.0. So the fine-tuning does help. It pushes the cliff further out.
But it doesn't prevent it. The cliff is still there for all of them.
Exactly. And another key finding, the cliff happens earlier at lower look-ahead values when the number of branches B is higher. More choices make the deep reasoning breakdown sooner.
That makes intuitive sense. But what really caught my eye was this trivial case they tested.
Ah, yes, the chain graphs.
Tell us about that. What's a chain graph and why is it trivial?
So a chain graph is the absolute simplest structure. It's where B1, there's only one outgoing connection from each node. It's just a straight line. A goes to B, B goes to C, C goes to D, and so on.
So there's no searching involved, no decisions to make about which branch to take.
None at all. The model literally just has to follow the single available path. No look-ahead planning needed in the sense of choosing between options, no backtracking.
You'd expect near-perfect performance then, right? Just follow the line.
That's what you'd think.
Yeah.
But even in this ultra-simple case, when they made the chains really long, up to 336 steps deep, the performance still dropped off significantly.
Even just following a straight line.
Even then, this was a huge finding because it suggests the failure isn't just about the complexity of the search or look-ahead. There seems to be a more fundamental issue with tracking information and maintaining coherence over long sequential dependencies, even simple ones.
Wow. Okay, so structural depth itself is a problem, regardless of branching complexity.
It appears so, and this issue becomes even more pronounced when you switch to the natural language task.
Right, the natural language proof planning. How do the models do there?
The collapse was even faster, even more severe. The performance cliffs showed up at much lower complexity levels.
Lower than in the symbolic graph task.
Definitely. For instance, the top LRMs, R1 and O3 mini, started to break down somewhere between a look-ahead of L10 and L64. Remember, in the symbolic task, they could sometimes handle higher L values before collapsing.
And what happened after they fell off the cliff? Did they still get some partial credit, or was it just random noise?
That's another fascinating part. Often the accuracy didn't just drop to 0, it settled right around the level of random chance, which is 1B.
Meaning, if there were 4 branches, B4, the accuracy hovered around 25%.
Exactly, or 50% for B2. It strongly indicates that once the complexity threshold was crossed, the models basically gave up on systematic reasoning and just started guessing randomly among the immediate next steps.
Just picking one of the available options and hoping for the best.
Pretty much. It signals a total breakdown of the intended reasoning process.
Okay, this is compelling, but there's always that counterargument with complex tasks. Maybe the models just ran out of steam? hit their context window limit or the maximum number of tokens they could generate?
Yeah, the truncation error hypothesis. It's a natural question to ask.
Did the researchers address that? Could this just be a length limit issue, not a reasoning failure?
They looked into it very carefully, and the evidence points strongly away from token limits being the primary cause. First, they observed that the models, especially the LRMs, rarely actually hit the maximum allowed generation length.
Okay, so they weren't getting cut off mid-thought most of the time.
Right, but the killer evidence, the really counterintuitive finding, was about token usage. As the tasks got harder, as lookahead L increased.
You'd expect them to generate more tokens, right? Thinking harder, producing longer outputs.
That's what you'd think.
Yeah.
But they found the opposite. Completion token usage actually tended to decrease as L went up.
Wait, harder problems led to shorter answers? How does that work?
It suggests that when the complexity exceeded the model's capability, it didn't just struggle and hit a limit. Instead, it seemed to give up earlier. It would stop reasoning sooner, or perhaps conclude no path exists much faster, even if a path did exist.
So instead of trying harder and failing due to length, they were essentially recognizing defeat early on when faced with deep complexity.
That's the interpretation. It strongly supports the idea that this is a fundamental limitation in the reasoning or planning capacity itself, not just a resource constraint like token limits.
Okay, so we've established that they fail, and it's likely a reasoning failure. How did they fail? Did they look at the kinds of mistakes the models were making?
They did. They manually inspected the internal thinking tokens or reasoning steps generated by the R1 model, one of the best LRMs, on tasks where it failed.
What did they find?
The mistakes largely fell into two categories, contributing to what they termed propagation error.
Propagation error.
Yeah, the idea is that an error early on messes up everything that follows. The most common error type was type I, omission. This happened in 15 out of 20 failure samples they looked at.
Omission. So the model just missed something important.
Exactly. It failed to consider or include a necessary connection or step at some intermediate point in the path. It just skipped over a crucial piece.
Okay, what was the other type?
The other main one was type 3, hallucination. This was also very common, seen in 16 out of 20 incorrect path results they examined.
Hallucination.
Yeah.
Inventing things.
Basically, yes. The model would include an edge or a connection in its path that didn't actually exist in the input graph or axioms. It just made up a step.
And both of these lead to this propagation error.
Right, because whether you miss a required step or invent a fake one early on, that single local mistake completely derails the rest of the reasoning process. Even if all the subsequent steps the model takes seem logical based on that initial error, the overall solution is wrong because it's built on a faulty premise.
It's like that analogy you sometimes hear about building a bridge. If the first support pillar is misplaced, it doesn't matter how perfectly you build the rest of the bridge, the whole thing is compromised.
That's a great way to put it. The local steps might look consistent, but the global coherence is lost because of that initial misstep. The error propagates.
And they didn't just see this in their synthetic DeepRD dataset, right? They tried to validate this on real-world data, too.
Yes, that was important. They used the natural proofs dataset, which contains actual mathematical proofs written by humans.
What did they do with it?
They did a couple of things. In one experiment, they took existing proofs and deliberately introduced errors, then asked the models to find those errors.
Yeah.
Same pattern. The model's accuracy at detecting the errors dropped sharply as the length of the proof increased. Proof length here acts as a real-world proxy for lookahead or structural depth.
So longer, more complex real proofs were harder to debug, mirroring the synthetic results.
Exactly. And interestingly, they even found that just asking the models to verify correct unmodified proofs from natural proofs could cause problems if the proofs were long enough. The sheer length and potential noise in natural language proofs seemed to overwhelm the model's ability to track the logic consistently.
Which reinforces the idea that this structural depth limitation is a real phenomenon, not just an artifact of the synthetic data.
Correct. It seems quite fundamental.
Okay, this leads us to the really critical question, RQ3 in the paper. How complex are reasoning tasks actually in the real world? If these failures only kick in at super high theoretical complexities, maybe it's not a huge practical problem right now.
Right, that's the key practical question. So they analyzed the complexity distributions, the typical look-ahead and branching factors found in large real-world knowledge graphs like ConceptNet, pathway datasets like OGB, and also the natural proofs dataset itself.
And what's the verdict? Are real-world problems mostly simple or complex?
It's a bit of a mixed bag, actually. There's some good news and some bad news.
Let's start with the good news.
The good news is that the vast majority, the main bulk of connections and queries in these real-world datasets fall into the low complexity regime. They have low lookahead requirements, low branching factors.
So for most everyday, simple reasoning tasks, the current LRMs are probably fine. They operate well within their successful range.
That seems to be the case. They handle the common, simple stuff effectively, which aligns with their strong performance on older benchmarks that likely sampled heavily from this common, low complexity part of the distribution.
Okay, but you said there was bad news. What's the catch?
The bad news relates to that long tail again. While the majority of tasks are simple, the complexity levels where the models start to fail, say, lookahead values of L16 or L32, which cause problems in natural proofs, aren't some extreme outliers.
Where do they fall in the real-world distribution?
Those failure points actually correspond to roughly the 50th to 75th percentile of complexity in datasets like natural proofs.
Wait, 50th to 75th percentile. That means a significant chunk, like maybe a quarter to half of the moderately complex real-world proof verification tasks are already hitting the complexity levels where these state-of-the-art reasoning models start to break down.
That's the sobering implication. It's not just the absolute hardest problems. A substantial minority of tasks that you might consider reasonably complex, but still common, are likely beyond their current reliable capacity.
And what about the branching factor in the wild?
That adds another layer of concern. Some real-world knowledge graphs have nodes with thousands of branches. The experiments in the paper only went up to B16, and performance was already collapsing rapidly at that level. Branch factors in the thousands are completely uncharted territory and almost certainly far outside the model's success regime.
So this really confirms the core thesis, doesn't it? Current LRMs, even the best ones, are highly tuned to the low complexity reasoning seen in their training data. They're powerful there, yes.
Very powerful in that zone.
But they lack robust generalization. When faced with structural complexity, deeper look ahead, or more branches that goes even moderately beyond what they've been trained on, their performance doesn't gracefully degrade. It falls off that cliff we talked about.
It's a systematic, predictable failure based on structural limits. They're great at recalling or executing low-depth reasoning patterns they've effectively memorized, but they struggle profoundly with genuine deep planning and maintaining coherence in novel, complex scenarios.
So just making models bigger or fine-tuning them more with the same ROVR techniques on simple tasks probably won't fix this fundamental depth limitation.
The paper strongly suggests not. It seems we need fundamentally new approaches, new training methodologies that specifically encourage and reward robust out-of-distribution generalization for reasoning depth. We need models that don't just succeed because the test looks like the training data's complexity profile.
We need models that can handle the unexpected structural depths inherent in truly novel problems.
Exactly, especially if we want to rely on them for high-stakes applications like scientific discovery, mathematical theorem proving, or complex legal analysis where encountering novel, deep structures is the norm, not the exception.
Which brings us to our final thought, something for you, the listener, to chew on. This paper highlights a major gap, but the DeepRD generator itself might offer a path forward.
How so?
Well, DeepRD gives us a tool to create unlimited examples of highly complex symbolic reasoning tasks with controlled difficulty. The paper showed models failed dramatically on these. So here's the question. What if we deliberately fine-tuned models on these harder symbolic tasks within DeepRD? Could mastering high L&B in the symbolic domain actually transfer and improve performance on difficult natural language reasoning problems, the kind found in natural proofs or real-world science?
Bridging that symbolic to natural language gap via targeted complexity training. That's an interesting angle.
Could focusing training on the structure of deep reasoning, even symbolically, build a more robust underlying capability? What kind of innovative training strategies, moving beyond just scale or simple rewards, might finally help models conquer this complexity cliff and prevent that catastrophic failure when faced with deep, multi-step logic?
That's the multi-million-dollar question, isn't it? How do we build models that don't just reason well until they don't?
Something to ponder. Thanks for joining us for this deep dive.
Thanks for having me.